Up until this time, we've been finding the derivative of functions. In 3.7, we're going to look at what happens if we don't have a function. And that's when we're going to be using implicit differentiation. So implicit differentiation is typically used when we cannot explicitly solve for y. Let's go ahead and look at an example. Notice in example 1, if we were to graph y squared equal to x, that would not be a function. That's going to be a parabola that opens to the right. So 1, 2, 3, 4, let's see. Let's go ahead and graph this. Forgive my squishy hand. That's a terrible graph. Anyway, so when I look at this graph, if I were to look at part A in this question, it says to find the equation of the line tangent to the curve at 1, -1. So that's my x, that's my y. So at 1, -1, I'm here at the bottom of the parabola. And if I were to draw the tangent line at that point, it would kind of look like this slanted line. It has a negative slope. Well, I do have a point, right? I have the point 1, -1. So what I need to find the slope of the tangent line, which means I have to find the derivative of this function. Only I have a problem, because this is not y equal to something. This is y squared equal to x. So in order to find the derivative, I'm going to need to break up my graph into two pieces. Okay? If I solve this for y and square root both sides, I have y is equal to plus or minus the square root of x. So notice that the top part of this graph is y equal to the square root of x. And the bottom part of this graph is y equal to negative square root of x. So if I want to find the equation of the tangent line at 1, -1, I have to use the bottom part of the graph. I have to use y equal to negative square root of x, or y equal to negative x to the 1/2. So when I find the derivative, which would give me the slope of this tangent line, the derivative is equal to negative 1/2 x to the negative 1/2, or negative 1 over 2 times the square root of x. So remember, I was supposed to find the derivative when x is equal to 1, which gives me negative 1/2. So the slope of my tangent line is equal to negative 1/2. Now that I have the slope of my tangent line, I can write the equation of the line, which would be y plus 1 equal to negative 1/2 x minus 1. And then if we're solving for y and writing it in slope-intercept form, we would have negative 1/2 x plus 1/2 minus 1, or y equal to negative 1/2 x minus 1/2. All right, so we got the slope, or we got the equation of the line tangent at the point 1, -1. But in order to do that, we had to split our graph up into two pieces and figure out which piece we needed to use. In part B, it says to use implicit differentiation to find the derivative and then verify the slope from part A. Sorry, it should just be slope, not slopes. So let me show you how we compute the derivative if we don't have a function. So let's go back to our equation y squared equal to x. I'm not going to solve this and break it up into two pieces. I'm going to take the derivative as it's written. And it involves using the chain rule whenever you see y. Okay, so remember this is the quantity y squared. I'm going to take the derivative of the left-hand side by bringing the 2 in front, so 2y, but then it's the chain rule. I have to do the derivative of the outside times the derivative of the inside, which is dy dx. But on the right-hand side, since x is the variable, the derivative of x is just 1. So whenever you take the derivative of y and you're using implicit differentiation, you have to use chain rule and do dy dx. Now I need to solve for the derivative dy dx by dividing both sides by 2y. So now I have my derivative. Remember, we were supposed to be evaluating this derivative at the point 1, negative 1. Notice my derivative doesn't have an x in it, it has a y. So I need to plug in the negative 1 for y in the derivative. And then the derivative is going to be 1 over negative 2. Okay? And that checks out. That's the slope of our tangent line from part A. So like the chain rule, when you do implicit differentiation, it's just something that you need to practice and get used to. So let's do some examples. If I want to find the derivative of y minus y cubed equal to 4x squared, well, I take the derivative of y, which is just dy dx, minus, but then I have to be careful with the y cubed, because this is the function, we're treating y as if it were a function, the function y to the third power. So it's going to be 3y squared times the derivative of the inside, which is just dy dx. On the right hand side, that's just x, so I take the derivative as usual, and that's 8x. So now we need to get the derivative by itself, the dy dx by itself. This is just going to be algebra. And this idea of factoring out the dy dx will come up a lot. So if I factor out the common dy dx, I get 1 minus 3y squared in parentheses equal to 8x. So to get the dy dx by itself, all I have to do is divide both sides by 1 minus 3y squared. And then this would be the derivative. Okay. All right, let's do it again. In part B, I have x squared times y equal to square root of y, which would just be y to the 1/2. Right? We do have to be careful. Because this is x squared times y, I'm multiplying two functions of y. I need to use the product rule. This is the most common error that people make when they're using implicit differentiation. They don't use the product rule where it's appropriate. So if I had to take the derivative on the left-hand side, I'm going to take the derivative of x squared, keep the y, plus keep the x squared, take the derivative of y. Okay? That's going to be 2x, keep the y, plus keep the x squared. The derivative of y is dy dx. Now just a note that you don't have to use dy dx. Remember, you can use dy dx equal to y prime, which is less writing. So that's going to be equal to, on the right hand side, we're treating y as if it were the function, so the 1/2 comes in front, keep minus 1/2 times the derivative of the inside, which is dy dx. Okay, so now I have to solve for dy dx. I think I'm going to move my dy dx's over to the right, because that will keep the 2xy positive. I don't like working with a lot of negatives. So I'm going to rewrite the 1/2 y to the negative 1/2 as 1/2 square root of y times dy dx. And then I'm going to subtract the x squared dy dx from both sides. Now I have all my dy dx on one side. I'm going to factor out. So again, remember this idea of factoring out the common dy dx happens almost in every one of these problems, especially where you have to use the product rule. So we're going to have 1/2 times the square root of y minus x squared. The last step would be to divide both sides by 1/2 square root of y minus x squared to get 2xy divided by 1/2 times the square root of y minus x squared equal to dy dx. Technically, this is not simplified because it's a complex fraction. So I would have to multiply everything by 2 times the square root of y to get rid of the complex fraction. And that would just be on the left-hand side. But it's okay if you stop here. Now on my lab, they may have you take it a step further. But I'm okay if you stop here on an exam. All right, let's do some more examples. In example C, I have sine of x times y is equal to the square root of y. Again, the square root of y we can write as y to the 1/2. So this again is a common error that the x and the y, you need the product rule. But I have another issue as well. I have sine is the outside function, x times y is the inside function. I have to use the chain rule. On the left-hand side, remember what the chain rule says. The outside function sine, I take the derivative of the outside, inside stays the same. So this becomes cosine of xy times the derivative with respect to the variable x of xy. And then on the right-hand side, this is just going to be 1/2 y to the negative 1/2. But remember, it's dy dx. Okay. I have cosine of xy. Now when I take the derivative here, it's product rule. Because it's x times y. When I take the derivative of x times y, I'm going to put this in brackets. The derivative of x is 1, y stays the same, plus x stays, derivative of y is dy dx. And then that's going to be equal to 1/2 times the square root of y times dy dx. Okay, so I have to get dy dx isolated by itself on one side of the equal sign. The problem is that I'm going to have to first distribute the cosine of xy. So I'm going to put the y in front. Cosine of x times y plus x times dy dx times cosine of x times y is equal to 1/2 times the square root of y times dy dx. And now, so far, all we've been doing besides the derivative is a lot of algebra. And unfortunately, calculus is a lot of algebra. I'm going to subtract the x dy dx cosine xy from both sides and bring all the dy dx over to the right. Again, I'm only bringing it over to the right because I don't like having negatives. I don't want to make the y cosine xy negative. So this is going to be 1 over 2 square root of y times dy dx minus x times dy dx cosine of xy. All right, so on the right hand side, factor out the dy dx, And what's left over in parentheses would be 1 over 2 times the square root of y minus x cosine of x times y. So to get the dy dx by itself, I'm going to divide by that hot mess. So we're going to get y times cosine of xy all over 1 minus 2 square root of y minus x cosine of xy. And again, you could stop here. Especially on an exam, I wouldn't have you simplify that complex fraction on the left-hand side. So you may stop here. All right. So let's do a few examples where we're looking at tangent lines. So I really want us to understand how to take the derivative here and apply it to finding equations of tangent lines. In example 3, we're looking at y squared minus cosine of x is equal to x. Okay, so that's not a function because of the y squared. So we're going to have to verify that 0, negative 1 is on our curve. Okay, so we're just putting in negative 1 for y and squaring it minus cosine of 0. The question is that equal to 0? That's what we need to verify. So we have 1 minus 1 equal to 0. Yes. The point 0, negative 1 is on our curve. Part B. Find the equation of the line tangent to the curve at the point 0, negative 1. Well, we have a point. All we need is a slope. So we need to find the slope of the tangent line. So what is this? Well, we have to find the derivative. But since it's a y squared, we're going to use implicit differentiation. So it's 2y dy dx plus cosine of x. Derivative is negative sine x, so this turns into a plus sine x equal to 1. So if we were to solve for dy dx, that means I'm going to go ahead and subtract the sine from both sides and then divide by 2y. So I have 1 minus sine x over 2y. That's the derivative. Now I need to evaluate this at the point 0, negative 1. So notice that this derivative has both an x and a y in it. And that often happens when you use implicit differentiation because it's not a function. If it were a function, the derivative would only have x. When I evaluate this, it's going to be equal to 1 minus sine of 0 over negative 2. And then sine of 0 is 0. So this becomes negative 1/2. And the equation of our tangent line is going to be y plus 1 equal to negative 1/2 x. And usually we would solve that for y. So I'm just going to minus the 1 from both sides. to get the equation of my tangent line. All right. Now when we look at part C, we're supposed to find the equation of the normal line to the curve. So remember, the normal line is perpendicular to the tangent line, which means the slope of the normal line is going to be the negative reciprocal of the slope of the tangent line. So the slope of the normal line is positive 2, and the equation of the normal line at the point 0, negative 1 would be y plus 1 equal to 2x, or y equal to 2x minus 1. So this idea of normal lines, or lines that are perpendicular to tangent lines, is going to come up in this last example for this section. We're going to talk about what it means for curves to be orthogonal. Okay? So curves are orthogonal if at every point of intersection, so every point in which they intersect, their tangent lines are perpendicular. So every point that these two curves, x squared plus y squared equal to 5 and y equal to negative 2, wherever those two curves intersect, their tangent lines will be perpendicular. So first of all, let's go ahead and sketch these curves. So in part A, and this is just a sketch, okay? Nothing fancy. X squared plus y squared equal to 5 is a circle, centered at the origin, with a radius of the square root of 5. And y equals to 2x is a line. Now, clearly this is pretty bad, but close enough. So that would be y is equal to 2x. It's this line, and this would be the circle x squared plus y squared equal to 5. So I sketched the curves. In part B, we're supposed to figure out where these intersect. So to figure out where they intersect, I think the easiest thing for me to do is to look at x squared plus y squared equal to 5. Now remember that y is equal to 2x. So if these intersect, what I can do is I could replace the y. Oops, sorry, this is supposed to be a plus. Replace the y with 2x and square that. We get x squared plus 4x squared is equal to 5. 5x squared is equal to 5. So x squared is equal to 1. And then we have x is equal to plus or minus 1. So the points where they intersect are actually going to be if x is 1, y is 2. If x is negative 1, y is negative 2. So these are the points of intersection. I'm going to go ahead and mark this on the graph that we had. We would have the point 1, 2, and negative 1, negative 2. And that looks correct. So I guess my algebra is correct. So the last part is to compute the slopes of the tangent lines at those 2 points of intersection, and then determine if these are orthogonal, if these curves are orthogonal. What that means is I'm going to have to take the 2 equations, compute the slopes of their tangent lines at the point 1, 2, and negative 1, negative 2, and see if the slopes of those tangent lines are perpendicular. So first of all, if I look at y is equal to 2x, and I only chose that one because it's easier, because the derivative is just 2. So that says it doesn't matter what point I'm at. I could be at the point 1, 2, or the point -1, -2. The slope of the tangent line, which is just the derivative, is equal to 2. Okay? So let's look at x squared plus y squared equal to 5. Unfortunately, to compute the derivative, I'm going to have to use implicit differentiation. So the x squared becomes 2x plus the y squared becomes 2y dy dx, and the derivative of 5 is 0. So if I solve for the derivative by subtracting the 2x and dividing by the 2y, I get the derivative is equal to -x over y after I reduce that fraction. Okay, so let's look at this derivative. At the point 1, 2, the slope of the tangent line is going to be -1/2. At the point -1, -2, the slope of the tangent line is -1/2. Okay, and that's enough for us to say that the curves are orthogonal, because at the point 1, 2, the tangent lines are perpendicular. Their slopes are negative reciprocals of each other. And at the point -1, -2, the tangent lines are perpendicular. So thus, the curves, I have to make some sort of conclusion after all this work, the curves are orthogonal. Okay, so that's it for this section. Again, like with the chain rule, implicit differentiation is something that you just need to practice. Okay, and